Traditional computer science approaches factorization as a problem of arithmetic magnitude. Trial division and similar methods test divisors sequentially, treating the integer as a linear list of potential candidates. Classical optimizations like Fermat's factorization focus on the gap between the two prime factors. However, as that numerical distance increases, the computational cycles required to bridge it grow exponentially. Hedys-Arcuna's sought fractal, or Fractal Leap, moves away from this sequential arithmetic search. This method utilizes topological relativity. It treats the semiprime not as a number to be divided, but as a coordinate mapped within a geometric landscape. Identifying these coordinates transforms a global search into a local identification of geometric resonance. The algorithm projects the semiprime into absolute space, calculating a target index n by taking n, dividing by 3, and rounding down. This target matrix is defined by the generating function. F of n equals 3n plus 3 minus negative 1 to the n over 2. Within this space, even indices generate the pivot families. They form a distinct geometric cluster in the matrix. Odd indices generate the satellite families, which fill the remaining topological space. Because the parity of the target index n is known, the algorithm identifies the topological state of the hidden factors, whether they are both pivots, both satellites, or a mixed pair. The algorithm converts the integer into a precise set of coordinates defined by their geometric properties. Even within this topological matrix, scanning every node from 0 is computationally impossible for large integers. To bypass this, the algorithm calculates a basecamp coordinate, labeled I-opt. This coordinate is found by calculating the square root of n over 12. This fractal leap terminates near the hidden factors, bypassing the trillions of empty nodes that slow down classical searches. From this basecamp, the algorithm determines the residual delta, r. R represents the exact physical distance between our calculated basecamp and the true coordinate of the semiprime. Factorization is now a matter of calculating this local variance. The final extraction requires finding the precise coordinate offsets, x and y, that resolve the residual delta. The first resolution path is the linear method, which uses a localized Diophantine equation to scan for resonance. This Diophantine probe uses the parity of the basecamp to set local force coefficients, F1 and F2. The algorithm iterates locally along the y-axis, checking each node until the equation returns a clean integer for the x offset. The force coefficients, F1 and F2, shift depending on whether the basecamp sits in a pivot or satellite cluster. For numbers with extreme asymmetry between factors, the algorithm employs the quadratic method. This approach treats the coordinate search as finding the roots of a second-degree polynomial. It identifies a discriminant, delta, that forms a perfect square. Finding this perfect square yields the roots x1 and x2, which correspond directly to the index coordinates of the two prime factors. Factorization becomes a deterministic mechanism of local resonance, largely unaffected by the total size of the factors. Cryptographic keys use varied numerical topologies, making it inefficient to rely on one mathematical path. To handle this, industrial implementations use the Armada TIA, a multi-threaded deployment of the algorithm. Thread 1 acts as the infantry. It performs a quick linear sweep to eliminate small, trivial factors that might otherwise waste the resources of the more complex solvers. Thread 2 is the sniper. It performs the direct fractal leap to the matrix center. This is calibrated for RSA keys, where factors are often placed near the square root to resist Fermat's method. Thread 3 is the heavy artillery. It handles hyperasymmetry by using multipliers to balance the matrix, folding the space to bring distant factors into range. The moment any one thread identifies a resonance, the CPU terminates the other processes. This ensures that the time required for factorization is always dictated by the most efficient mathematical case for that specific number. We can see this efficiency in action with the Mersenne number M29. M29 is highly asymmetrical, a structure specifically designed to exhaust classical factoring algorithms. For M29, Fermat's method requires over 2 million iterations. Pollard's row is more efficient, but remains probabilistic, meaning its success depends on random chance. The fractal leap, using matrix balancing and the quadratic probe, converges on the factors in exactly 80 iterations. Because computational effort isn't tied to integer size, the assumptions protecting asymmetric encryption have changed. We must consider the algorithm's limit. What happens if the target is a pure prime number? A pure prime number has absolutely no internal resonance. In the absolute space matrix, it appears as a complete topological void. Without resonance to guide it, the probe must scan backward from the base camp to the very edge of the matrix to prove that no factors exist. In this specific case, the algorithm reaches the standard mathematical limit for primality testing, which is the square root of n. The fractal leap respects the absolute limits of pure primes, but it maps the geometry of composite numbers with high precision. In this era of topological mapping, the security provided by large integers is no longer